piece with a light inextensible string running over it. It will always be a light inextensible string, and it will always be a frictionless pulley. Then they say when the masses are released, there's the coefficient of kinetic friction is 1.5 on the 1.5 kilogram mass piece is 0.4. Okay, so there's definitely friction. Right, now you scan the questions. What did they not ask? Kutluano. What did they not ask? And are you going to leave it like that? No, you are not going to leave it like that. You are definitely going to draw free body diagrams for both objects. Sia, give me the free body diagram for the 1.5. Okay, then Tsepo for the 2 kilogram. Say again. Towards the center of the earth. And? Wait. What? Wait. For the 2 kilogram. Is the rope going left? The rope is going up. Wow. Can I say that these two forces are equal? Say again, sorry? No, they are not equal. Why not? Okay, no, that's not the reason why you can say that. The reason why we say that is they did not say the object is at rest or moving at a constant velocity. If they said that, then they would be equal to one another. But we are going to assume they're accelerating because they asked at question 5.2, calculate the acceleration. Right, then I see very little highlighting happening. I have drawn these things. Watch out. I told you I'm a very verbal marker. And that comes out in my marking. You don't want to make me moody. I'm already moody due to certain things. So what are you going to highlight? How are you going to highlight? For which object? 2 kilogram. Yes? Is it the same as these ones or the same as those ones? They are the same as these ones. Why? Because, and I showed that to you the other day, is if this one moves to the left, this one goes up. This one goes down, this one goes, no wait, this one goes left, this one goes down. This one goes to the right, this one goes up. So this one's up and down, so this one is left and right. So that is why they are highlighted the same color. Or what you can look at always is the tensions. Because it's the same rope, it must be highlighted the same color. So since this tension is highlighted yellow, this tension must be highlighted yellow. Alright. So then this one is up and down like that. Okay, now at question 5.1, they ask, calculate the size of the kinetic frictional force that acts on the 1.5 mass piece, and it counts 3 marks. Tells you formula, substitute, answer. It can't be difficult. Okay, so the kinetic frictional force, that's what they asked for. They gave us the coefficient as 0.4. And if you look at your data sheet, there's a formula that connects those two things with one another. Or no. What does this N stand for? Say again. the normal force. Okay, so the normal force for which object? They ask specifically for the 1.5 kilogram mass piece. So we want that normal force there. Okay, so they want kinetic frictional force. They gave us the coefficient of friction. We must calculate the normal force. Ntando, how are we going to calculate the normal force? That normal force there. No. Como so? Say again. What did you do? Ntando is actually your question. 50-50. Ask the audience. Call a friend. Audience? Anyone in the audience? Khali. How did you get to that? Hoekom? Two reasons. Yes, the object is stationary in the vertical. So this object is not moving up or down. So it's stationary in the vertical. And there's only two forces. So that is why this one is equal to that one. It's not always that way. It's for this scenario, that one. Okay, so it's equal to Fg. How do we calculate Fg? It's mass times 9.8. Okay, so that is why we can say this here, the coefficient is 0.4. We want the kinetic friction, and the normal force is 1.5 times 9.8. And Bukamuso, if you calculate that, what do you get? No. What do you want to do? You want to get rid of that, so you're going to multiply. Did you type in 0.4 times 1.5 times 9.8? That is what you should do. Yes? 5.88, and the unit for frictional force? No. Force. N stands for what? What is this chapter's name? My aim in life is to promote more learners to become teachers. But I don't think you help with that aim. Who wants to become a teacher in this class? Yoke. Really?
It's an option.
What teacher? Teacher for what?
Physics.
Okay. Right, 5.2. It says, calculate the size of the acceleration. So acceleration, Newton's second law. Oh, I said Newton's second law, Tatu. Newton's second law in words. Prachtig. Sure. Okay. So 2 marks definitely in the test for her. Okay. It says you must use Newton's second law to calculate the acceleration. They say you must use look at this object, that object, and then do it simultaneously. I'm not going to give you these instructions in the exam. Okay. You must know that since we have 2 objects, we must do that. Okay, so Newton's second law, F net is equal to M times A, F net is equal to M times A, Please remember in a test or exam, write this underneath one another, not next to one another. Then we're going to look at the yellow forces because we're assuming it's going to accelerate in that direction. Okay, so since it's accelerating to the right, we choose to the right to be positive, and down, we choose down to be positive. Then we have T minus Fk is equal to M times A, and here we have Fg minus T is equal to M times A. Make sure about your directions that you subtract the correct things from one another. So we have T minus, now we've already calculated the friction there, so it's going to be 5.88, and remember, in a test we mark with your mistake. This is for the 1.5 kilogram block, so it's 1.5 times A, so you have T is equal to 1.5A plus 5.88. Then for the 2 kilogram block, gravity is 2 times 9.8 minus T is equal to 2 times A. So you get 19.6 minus 2A is equal to T. Yes? So both are equal to T, so now we put them equal to one another. Is equal to 19.6 minus 2A, and we get 3.5A is equal to 13.72, and you get the acceleration to be 3.92 meters per second squared. Can I see who got this right? Mooi. They're all for 5 people out of this whole class. I did count your hand, thank you. 5 people, and this is easy peasy. If you get a question like this, you should thank your lucky stars. And this is not the first time we've done it. Not the second time we've done it. Not the third time we've done it. This is the last time we're doing it. So I consider this or you to be perfect in this type of question right now. So if you are not, you must go practice at home. Any questions? Ma'am, I did like this. Here I made a mistake. Can you please explain again? Yes. Yes. Okay, so then obviously everything is wrong. But you put up your hand. But anyway, in which direction is it moving? Down. So that is why you need to take down as positive. Because what you basically said when you chose up to be positive, okay, this one is accelerating this one, right? And then you said, but this one's going up. So you said this is happening. Is that true? No. So your direction must make sense with the motion. Okay. Any other question? Right. Then they ask at question 5.3. They say there, this surface is now replaced with a frictionless surface, and the two mass pieces are going to accelerate again. Now they ask, how will the acceleration compare with the one that you've just calculated? Increase, decrease, remains the same, or bigger as, smaller as, or equal to? And quickly, or give a reason for your answer by referring to one of the laws. Rory, what did you say? It's true, greater than, why? Okay, you started right and then you went wrong. Okay, so bigger as is the same, greater than is correct. Then you refer to Newton's second law. So you can say Newton's second law, or you can write down the formula, or you can say in Newton's second law the acceleration is directly proportional to the net force. What happened when there's no friction? The net force is increased, because if there's no friction, then there's nothing minusing, subtracting from the net force. Are you with me? Okay, so then the net force is bigger, thus the acceleration is bigger. So when friction is removed, net force increases. So there is your 3 marks. For greater than, for referring to the formula, either saying Newton's second law or writing down the formula, and then for saying when friction is removed, the net force is increased. That is your 3 marks. Yes?
How about less than?
Say again?
Less than.
Less than is fine? No. Less than is opposite than greater than. Yeah, but they ask how does frictionless compare to friction? Frictionless is greater than friction. Alright, then yes? Say again? Okay. You'll get 2 out of 3. Did you say friction is removed? Did you say net force increased? No, not less force. What force? You must be specific. Less frictional force. Okay. That's 3.1. 5.3.2. They say that the 2 kilogram mass piece reaches the ground before the 1.5 reaches the pulley. So they say basically that pretend the chair is the floor. They say that when you get here, okay, we're here, it's accelerating, but this reaches the floor, and this one is still moving. So now they want to know what type of motion do you have with this 1.5? The 1.5? 1.5? Yeah. So what's happening is this one reaches the ground first, and then this one is still moving. What type of motion? Accelerating, decelerating, moving at constant velocity. What do we have? Okay. Now remember, there's no friction. Okay. What type of motion will it have? Khali, did you say? It will have constant velocity because there's no tension to increase velocity. There's no tension to increase velocity or no tension to cause acceleration. So nothing is making it go faster, and no friction slowing it down. If there was friction, it would have been going slower. But since there's no friction slowing it down, it's just going to go on and on and on and on and on. They said at question 3, 5.3, the rough surface is replaced with a frictionless surface. So there's now no friction. They tell you there's now no friction. Read the question. Yes. Okay, maar loop net een van julle, nie albei nie. Alright, then grade 11. Let's go to Newton's gravitational law. Hey? This is his 4th law. Yes. Page 11. Okay. Newton's gravitational law. Now, you remember extra classes yesterday? It's linked to that idea. I told you yesterday that if you have 2 magnets and you put them close to one another, they will attract each other. Yeah. Right? The bigger or the stronger the magnets, the bigger the attraction. And the closer they are to one another, the stronger the attraction. The further they are from one another, the weaker the attraction. Okay? The same concept idea here. I'm going to read and then explain again. It says, The weight of an object is the gravitational attraction force with which the Earth attracts the object towards the center of the Earth. Okay, so it says the attraction force. Now it says, according to Newton's third law, now let's just stop. What is Newton's third law? It says, when A exerts a force on B exerts a force on A, equal in size, opposite in directions. Yes? Simultaneously at the same time. So according to Newton's third law, if the Earth attracts an object, the object attracts the Earth. Right? So that gets then to Newton's gravitational law. So that in the block is the definition. It says each body, now body is like a planet, sun, moon, stars, rock, person. Each body in the universe attracts every other body with a force that is directly proportional to the product of their masses. Product means multiply times. Product of their masses, and inversely proportional to the square of the distance between their centers. Okay, so Newton's gravitational law says each body in the universe attracts everybody with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, so it basically says the force is directly proportional to the product of masses. So two objects, two masses. And it says force is inversely proportional to the distance, we're going to look at the radius, the distance between their centers squared. So if you combine those two ideas, you get that formula. Okay, so you'll see the only thing that is different here, just wait a minute, I'll be with you in a moment, is this G here is not in my F that I said there. And you'll also see this G there is also not on your data sheet. Okay, so it doesn't have to be there. I'm putting it in brackets because that G I'm going to refer to hopefully today or in the next lesson. Okay, then, ma'am, what about this G there? That is the universal gravitational constant. Okay, that's on your data sheet, a constant that's on your data sheet, so you do not have to go study it. And the reason why it's in there is, like I explained yesterday, if we have these proportional symbols, we're not very happy because then we can't do calculations. We want an equal symbol. And to put in an equal symbol, they draw a lot of graphs and they get a gradient like that is constant. And the value of that gradient is G 6.67. Okay. So don't worry about how they got to it, blah, 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 blah. Just know that is the formula and that G is a constant on your data sheet. All right. Now, quickly memorize this definition because after I'm done with them, I'm going to ask. You'll need to say this definition. Who is going to athletics tomorrow? Thank you. All right. 14, go for it.
Each body in the universe will attract another body in the universe with a force that is directly proportional to the product of the masses and inversely proportional to the distance
Between their
centers. Square.
Baie mooi. Nee, Carlo, go. I'll start for you. Each body in the universe will attract another body with a force that is. What are the masses? What are we doing with the masses? Of the masses. And inversely proportional distance between them. squared. Letter B. Each body in the universe will attract another body with a force that is. To the between the squared. All right. So, what I want you to think of for this formula, and also for the electrostatic law, is if you have, now this is just a story generalization, if you are in a relationship, alright, if it is a long distance relationship, does it last? Yes. Alright. So the idea here is the further apart you are from one another, the less you know what the other person is doing, the less you see each other, the smaller the chances are of relationship. Okay guys, this is just a story. I had a long distance relationship for a year and I'm married that man. So it's not alright. But that's the idea. Okay, and the closer you are together, the more loving they can be, so the stronger the relationship. And then my father has a firm belief that a woman should have something to touch. So the bigger the objects, the bigger the loving. The smaller the objects. Who was this for? All right. Okay, grade 11 is just a story to help you to remember. Okay? No, I'm not going to repeat. All right, let's see how we're going to apply that. It says you have a sphere, a round object. The one is 6 kilograms, the other one is 4 kilograms. And they are placed at distance so that their centers is 2 millimeters far apart. And then I ask you, what is the force between them? Right, now in physics, we work with big objects, so we work with kilograms, that's fine. But in physics, we do not work in millimeters, we work in meters. So really, how do we go from millimeters to meters? -3, divide by 1,000. Right, so we have F is G. Now this formula is on your data sheet. You do not have to memorize it. G is a constant on your data sheet. So that is 6.67 times 10 to the power negative 11. The first mass is 6 kilograms, 4 kilograms. Over the distance is 200 times 10 to the power negative 3. Something is missing there. Let's see what is missing. Squared. What did I say said yesterday? How many people will forget that square?
6,000.
I think about in this class, I'm going to say about 3. Who will forget? I want to bet. If I am right, you, the class, right, just wait. If you want to bet. If you want to bet, you must buy the whole class sweets. If I lose, then I'll buy the whole class sweets. No. 2 rand lollipop. We said 3 people in this class. No, not let's make it. That was my arrangement. Do you guys trust Clooney? No.
MOT. Mashallah.
No.
He's on the line.
Okay. Yes?
4.00
Times 10 to the power of?
negative 8.
And the unit?
Units.
You can only call Bukamuso.
Yes, Mama, Kulin.
Bukamuso, what's the unit? For force.
Oh, N.
N stands for?
Mine is in Kulum.
No, it's not Coulomb, it's Newton's with forces. You're thinking about the next chapter. Alright. Then grade 11. A force is a vector. A vector has size and direction. Now, since there are two objects, and we said in the law, any two bodies in the universe will attract one another. So this force is attracting.
So, we always write that we have to use that.
If they ask for the direction. Then the next one is a multiple choice question that you will for certain get 4.002. You will for certain get in a test or an exam from now on until the end of matric. This is a multiple choice type of question. So this type of question you must understand and be able to do. Okay, it says there. An object with a mass m experiences an attraction force of F on the surface of the Earth. What will the size of the attraction in terms of F be if the object is at a distance of 2r, 3r, blah, 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 from the center of the Earth? Okay, so they say there you have the Earth and the person is standing there. And that distance there is r. Okay, so we're going to do 3 scenarios. So the first scenario, we have m over r squared. Okay, now ma'am, where's that m1, m2 business that we just did? I'm just not to have m1 and m2. Small m is the person, the object, you. Big M is the planet. Okay, just to simplify. The small m person, big M planet, and their distance r, and then I say the force between them is F. Now they say you take that person up, it flies, so that the distance there is 2r. And they want to know how that influences the force. Now what did we say about long distance relationship? The further away, the smaller the force. So we're thinking we should get a smaller answer. Okay, let's check. We have F2, because it's the second F, is GMM, because the mass of the person did not change, the mass of the Earth did not change. And now we have over 2r squared. I've made a mistake with how I've written that down. What is the mistake? Kutlano. Wait. Just r squared. Okay. Remember, if this was 1,000, then this now is 2,000. You want to square the whole 2,000. You don't want to say, okay, 2,000 is actually 2 times 1,000, and then I'm just going to square the 1,000. You want to square the whole distance, the whole radius. So that whole 2r you are going to square. Okay, and that is the trick in this question. So that then changes to GMM over 4r squared. Now I want this to look as close to this as possible. What's the only thing that is different? It's the 4. So I'm going to take the 4 out, and then I have a quarter, because dividing by 4 is the same as a quarter. Nee? Wiskunde? Then we have GMM over r squared. Then I can say, okay, then this looks very similar to that. Looks exactly the same. And we say this is equal to F. So then this is equal to F. So then I have that to be equal to a quarter F. So what happened to the force? The force decreased by a factor of 4. It's 4 times as small. We said the further away they are from one another, the smaller the force. Okay, let's see, they say we now take it so that it is 3r away. Okay, so now we have GMM over 3r squared. What's wrong, Sia? What must I do there? The bracket, do not forget that. 3 squared gives you what, Seppo? 3 squared gives you what? 9. So again, you want to take out that 9. It becomes a 9th. Then you have GMM over r squared. And again, that looks similar to that. So it is a 9th F. Right, you get the idea? I can ask it in a multiple choice. All right. Grade 11s. I'm going to stop there for today.